Waves. Waves review again for the first time. Put your hand in front of you like this. Wave. Not like this. Not like this. This. What kind of wave is this? Well, it's very nice, Jeffrey. That is called a transverse wave. What's the other kind? Longitudinal. So put your hand like this. Now, if you're sitting in the water, a water wave is a transverse wave, right? If a wave goes through our classroom, are we moving with the wave? Colin is shaking his head. What are we doing?
Up and down.
We're going up. We're going down. I'm resisting the temptation to tell you so many wave stories. Ben just was like, do it. And Jake was like, keep it. One time on New Year's Day, I was in Maui, and a swell hit, and it was like 25-foot waves. And my brother-in-law took me out there, and I almost died. It was really close. And I remember being out there, and the waves were so big, and I was going up, and I could see, and then it would go down, and it was like these black walls of water like this. Anyway, you're going like this. That's it. That's what the atoms in the water are doing, right? They're just oscillating. So if the atoms of the water are not moving with the wave, then what is the wave?
Energy.
Good. The wave is energy. Where does the energy come from with the water wave? Kind of from the sun. What makes the water turn into waves? Wind. Very good. The wind makes the waves on the water. And there will be like a storm up in the Aleutian Islands or something, and there's a big storm, and you get all these waves. Are all the waves the same size? No. Are they the same speed? No. So how come when you're out on the coast of Tofino, you get wave, 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 wave? How come it's uniform if all the waves are so...
Constructive interference between each other and destructive.
So you can have lots of constructive and destructive interference, right? What does that mean?
Superposition.
Put your hands like this, you have two peaks. When they come together, what do you get?
Bigger.
You get a bigger peak. If you have two troughs and they come together, you get a bigger trough, right? What if you get a peak and a trough come together?
Cancel out.
Right? That's which one of those is destructive?
That one.
It cancels out as destructive. Good. You can have that, but that's not why the waves are all uniform and come in with a real frequency. The reason is because they travel a long distance, and there is a relationship between the wave length and the velocity. Waves that are bigger travel faster, and so they come out of the storm and they're all big waves, small waves. It's a big mashup of waves. You know, like an Elvis and Drake song or something.
Should we first talk about simple harmonic motion?
No.
Okay.
And then when they go travel a long way, the fast waves all travel fast, and the slow waves travel slow. And so over a long period of time, what do you end up with? They separate out. The big waves all win. They're way out in front. And the smaller waves, the chopped stuff, is in the back. And so the big fast waves outrun the little stuff. And the fastest waves are in the front. So when you're in Hawaii and you get the storm, all of a sudden, just one day, it'll be like 30-foot swell. And then it'll get smaller and smaller and smaller as the waves from that storm roll in. How deep underwater do you have to be to not feel the waves? Or does it go all the way to the bottom?
You have to go lower than the amplitude, or that it's higher.
Yeah, kind of. So the wave base is 1/2 the wavelength. So if your peaks are 20 feet apart, if you go down 10 feet under the surface of the water, you won't feel the wave anymore. If you're just underneath, you'll be going back and forth. But if you swim down a bit, it'll be totally calm. Why doesn't it go all the way to the bottom? If the top is moving up and down, doesn't the whole thing move?
That would make the earth.
That would be something, wouldn't it? Be all these little vacuum pops on the bottom of the cushion. The energy dissipates as it gets lower. Right? What happens to the water in front of the wave when the energy is lifting the water up? Then what happens to the water in front of the water that's being lifted up? It gets pulled in, right? So if you're in the water, are you really moving straight up and straight down? How do you actually move? Yeah, it's a little bit of a like this, right? Well, it's actually a little bit diagonal is what it is. Okay, so that's waves, and if you know the frequency and the wavelength, what can you find? You can find speed, right? This is the universal wave equation. This being wavelength, this is frequency. So if you have a wavelength of 2 meters and you count 5 waves, you go down to Ambleside and there's a swell, which there never is because I take my class down there all the time and there's never a swell. But if there was a swell and there you have 2 meter wavelengths and you got 5 waves per second, what's the speed of your wave?
10 meters a second.
Yeah, this makes sense, right? If you've got 5 waves roll in, and each of them is 2 meters, you've basically got 10 meters of wave coming in every second, so that's your speed, right? What is this with light?
Speed.
So for light, it's a special pace. What determines the speed of a wave? So that's a formula, but what decides how fast the wave can go, Pran? Very good. Let's give Pran a call. It's the medium. So if you have a sound, and I say, ah, and then I go, ah. What's the difference in the speed with that one and this one? Nothing, they're the same, right? And so what happens as you run at someone yelling?
Doppler effect.
Frequency goes up.
The perceived wavelength shrinks, right? And so, but the speed is the same, so what has to happen to the frequency?
Goes up.
It has to go up until you hear this higher pitch, right? That's why when the race car goes by, it goes, "Rrrr." And what do we call that?
Doppler effect.
Doppler effect. Now you know the formulas, right?
Yes.
And the formula is different for moving source and for moving observer, and whether it's going forward or back, right? So there's like 4 different ones. Yeah.
There's a possible chance, I'm not sure, but that Doppler effect is just for HL.
It is.
Oh, okay.
Could be.
It is.
Really? They don't even make that. What does the SL do?
Yeah, that's what I was thinking. That was what I was thinking. I know this was
Weird.
myself.
Let's go through this.
Just do HL.
A pendulum is an oscillation, right? So it goes back and forth. Is a pendulum simple harmonic? What do you need for an oscillation? Oh, sun is locked up. Can we let her in? What do you need for an oscillation to be simple harmonic?
The acceleration is should be proportional and opposite.
So the frequency, there's a list here. Let's see if we
Always returns to the initial state.
First of all, the acceleration, this is like really small, but that's big. They always ask about this. The acceleration is proportional to the
Negative displacement.
negative displacement. This is your list, so I would remember this. Just memorize it, because they'll ask you, is this thing, they'll come up with a situation, they'll say, is this simple harmonic? So does it satisfy these 3 things? And even if you don't know, if you say these 3 things, they'll often just give you the mark anyways. So period and amplitude are constant. You understand what period is?
Yeah.
It is the reciprocal of what?
Frequency.
Frequency. So if you just do 1 over f, you can get the period. And the amplitude has to be constant as well. So if you're driving in a car and you guys probably have never felt this before, but in an old car, They used to be bouncy. So you go over a bump, and then your shock absorbers would go like this, and it'd be like, but it would dampen, right? Do you know what I mean when I say dampen?
Yes.
Okay, what do I mean?
It tapers off. It gets weaker and weaker.
Right, so it starts off a big bounce, and then this is dampened harmonic. That is not simple harmonic, because the amplitude has to be constant. Right? We kind of say that a pendulum is because we negate the friction in it for a little while, but in the real world it's not. The period has to be independent of the amplitude, so you can change your I should show you this, but we don't have time. But if I had a bunch of springs and they have mass all at the same height, and I pull them down different distances. So you get what I'm saying?
Yeah.
You have a spring hanging mass, and I got you to come up here, which I should have done, but I didn't teach you this. So, and you pull them all down different distances, and then you release. Which one would have the biggest period?
Yeah, all the same.
That's good. They're all the same. It doesn't matter how far you pull it down. The one you pull down more, how can that be? How can the period be the same? You pull this one down more, it has farther to get to.
Restoring force is harder.
Good. It's going to go faster on the way through, right? This one's going to go slower, and it's going to go. But the period is the same. Okay, so the period and the amplitude have to be independent, and then the displacement, velocity, and acceleration are sine or cosine functions of time. So if you start with a sine function, like if you start at 0, bless you.
Thank you.
What's the derivative of a sine?
Cosine.
Cosine.
Negative
Cosine.
cosine.
So if your displacement is sine, we start at 0. Sketch this on your paper, what's the velocity? Sorry, this is supposed to be time. This is t and x, so what's the pt? Eric, do that again. Starts high, that's what Angie did too. Yeah, it starts high, it comes low. Now, you get what that means, right? So you can know that a sine, the derivative of sine is cos, but why does it start up high?
Because when it's in the middle, it's traveling it's like the fastest.
Yeah, when it's in the middle, it's traveling fastest, and the slope of this graph is the steepest here. It's positive, right? So the slope of this is the value of your velocity graph. It's the derivative. So it starts here, and it goes like that, right? This being this negative slope, and then it goes up. I didn't draw it. Just draw it. Okay, and then what's the acceleration going to look like? What's the derivative of a cosine?
Negative sine.
Good. So you're going to start at 0 because this is flat, right? And then when it goes down, we would be negative, right?
Yeah.
Because it's a downhill slope, so you're going to be down here. And then it carries on like this. So this was sine, and this would be cos. This would be negative sine. So just flip sine. Okay. And they're all, the derivatives work. Okay. Ooh. So this is a nice graph because it shows the displacement and the velocity and the acceleration. They don't have to have corresponding amplitudes, but the phase differences have to be the same. And this is SHM. Frequency is 1 over t, and 1 over t, or 1 over f is t, and t is 1 over f, and f is 1 over t. Okay. Hertz, you know about hertz, right?
Yep.
Cycles per second. What does phase difference mean? Yeah, if you shift it, right? One example of simple harmonic motion is alternating current. So the current in the wires that are powering these lights goes back and forth with a fixed frequency. And if you graphed the intensity of the voltage, it would be a sine graph. And that graph, will you tell me, a sine graph is analogous to what type of motion? This is something you should all know and you should all have set for the exam, because if you can explain it, you'll get extra marks. Nobody knows? A sine graph, a simple harmonic motion, is analogous to what type of motion? Circular, yeah. You guys know. So if you spin this, you have a little tapey guy here going in a circle, right? And it's just going around, but if you move it this way, I don't know if you can see that, but it's going up and down and up and down and up and down. And if you graph that over time, you would get a sine graph, which is analogous to this. Yes, Kenta?
If there's 2 points on one wave that's like offset, does that mean there's a phase difference between them?
No.
No.
Between the points?
Yeah.
That's an interesting question.
Because I've had some on the exam.
So
There's
like
two
if
questions.
you
One's
have
exact
like
same, one's a no,
spot, like
one's
a
a
person here and a person here.
Yeah.
Yeah, you could say that they were. I think you could say that. You could say like this is pi over 2 difference.
Because in some years exams on the multiple choice, they say no, and some years they say yes.
Of course they do.
So I don't know.
So if they're riding the same wave, you would say the waves are the same.
Yeah.
They're in phase.
But the points are not.
But if you graphed this person's vertical position over time and that person's vertical position over time, they would be pi over 2 out of phase. So I think it would really depend on how they worded it.
Yeah, that might be one.
Definitely.
What is phase shift?
Phase shift is, so let's talk about it to do with current. So you have, let's say you have a hydroelectric dam and a penstock, and water comes down, and what does it do? Spins the turbine. And what do we get out of that? AC current. Because we have those loops moving through the magnetic field, right? And we get the up and the down. What does that really mean? What's actually happening? Honeycutt's going like this. So you're pushing electrons and pulling electrons. Pushing electrons and pulling electrons. So do the electrons ever get from the hydroelectric dam to us?
No.
No. They just get pushed back and forth. It's a Sisyphusian task. If you put 2 generators and they're both being turned, but the loops are at kind of 90 degrees. So one generator is turning like this and the other's turning like that. Does that make sense?
Yeah.
Then this one's going to be pushing while the other one's going to be pulling. Okay? And that's actually how it's done, and that's how the electricity is sent to us. We have, if you look out on the street and you look up at the top of the poles, there's 3 wires there. Why do we have 3? So 2 of them are hot, and 1 is a common. So you have to have a loop to go back to the dam, right? If there's no loop, nothing moves. So you have to have a way back, and the 1 is the common. So they both go into that common and go back to the dam. But the 2 that are hot are out of phase. So if you look at your, okay, don't do this. But if you go in your panel, your electrical panel, what's in there? If you open the door, what's in there? Well, there's circuit breakers, right? So you open the door and you see switch, 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 switch. Yes?
Yes.
Okay, if you want to get 240 volts, it will be you have to be careful because you can't match them up and have them be out of phase because it'll go to zero. You'll get nothing, right? So you have to make sure if you have a double breaker that's on your like stove or whatever, you have to hooch to one side of the panel that comes in like this, and then you have to hooch to the other side of the panel that comes in kind of like that. And if you open this up and take it off, you'll see 2 bars at the back. And those 2 bars are from the 2 hot wires. And they are 180 degrees out of phase. They're pi out of phase. So I'm making it more complicated than it is. If you're out of phase pi radians, then this is 1. And what's the other one going to look like?
No, it's the opposite, so down.
Right.
Oh yeah.
This would be pi radians out of phase. If you wanted to shift this forward, just say pi over 2, what would you do?
Sine, cosine wave.
Yeah, you would just pull everything forward like this far, right? Pi over 2 being 45 degrees, a quarter of a wavelength. And so you would just start this at this place, so it would be here, and it would go like that. We can draw it on the same graph. You could start here, and you just follow the wave up, and it just stays ahead of it the same amount every time. Your phase shift is this. It always moves forward the same amount. Does that make sense? That's all phase shift is. One thing to remember with waves and reflections, do you remember when is there a phase shift with reflection? Yeah, if you're hitting a denser thing, the wave tries to lift up the thing, but it can't, so what happens? It holds itself down, right? What if it's less dense? Then it just lifts the thing up.
But doesn't something else change, like the amplitude bigger?
When you go into the new material, your wavelength will change. So especially if it's light, because your frequency has to stay the same. Because if you have 60 hertz hitting a barrier, you have to have 60 hertz coming out. You don't, waves don't disappear or stay the same. But, okay, so when you throw light into a more dense material, what happens to its speed? It just goes down, right? It's like running into the mud in your wheelbarrow. Have I told you about the wheelbarrow? Okay. And that's why it turns, right? You have your wheelbarrow with your 2 wheels, you go at an angle towards the mud, but one wheel hits first, and it bogs down and you turn.
Wheelbarrows only have 1 wheel.
Oh, it's a special physics wheelbarrow. Can't tip over. And that's why you get, what's one way to think about it? Why you get refraction into the material. But you also slow down your velocity, right? So we said that c equals lambda f, right? This has to stay the same, but your light has, your c, your v has slowed down. It's not c anymore, right? It's c over v, I guess, right? What's the n? It's n, right?
Yeah, that's the refractive.
What's that formula, the Snell's law?
N1 over N.
I find this one easier to remember. N1 sine theta 1 equals N2 sine theta 2. This is for material 1, this is for material 2. What's the n's?
refractive index of the
That's the
substance.
refractive index of the material. So if you have, it's how many times the light is slowed down, I believe, right?
Yeah.
And it has to do with the density of the material. The more dense, the slower the light goes. So this would be, you would say this might be the angle of incidence, and this would be the angle of refraction. Where is it always measured off of?
The normal.
Yeah, you always have a normal, right? So when you get your light coming in, like this, which one of these, top or bottom, would be angle of incidence? This would be your angle of incidence, and then you always bend towards the normal, right? So what's the angle of refraction? This one. So if you're refracting, well,
that's only if it's denser.
yeah, I suppose that's true. Yeah, if it's less dense, it's gonna grow.
You're negative
that's true.
towards the normal.
So if it's bigger, more dense material, you get more refraction towards the normal. What if you're, and they ask this sometimes, what if this is water and this is air? You guys know how it works with the coin in the water and you try to,
Yeah.
or carry that. No? Yeah, no, not critical angle, but like, okay, so if Jeffrey's standing up here and he's looking down and he sees a coin on the bottom of the sink or whatever, right here, where is the coin actually?
Work forward.
A bit higher.
Would it be here or would it be there?
Maybe a bit lower.
You should be closer. You should
Work
be
it out.
closer to the-
You're gonna have to know
It's
this.
gonna bend towards the
What happens when you see something?
It's definitely to the left.
To the left?
No. To the right. It's to the right.
You guys don't know.
Well,
You better
it's-
figure it out.
It's just.
What happens when you see something?
Like,
Light's coming from here to you, right? So if the coin is actually here, your light comes from it up to here. Which side hits first, top or bottom?
top.
Oh, the top's gonna hit first. This is gonna hit first, and when it comes out into less dense, it speeds up, right? So this is gonna go woo and turn this way. And it's gonna come out like this, and Jeffrey's not gonna see it. But, or he won't see this light ray, right? But which light ray will he see? The one that came up this way, right? Top hits, and it comes out, and it's like, woohoo! And this goes faster, and it goes to him, and he sees the coin. But if the coin's really here, he doesn't see it here, right? He sees it as if it's out here. So if you look in, if you can do this at home, just fill up a sink and drop a coin in there, and take a ruler and try to stab it. And then I always do this with my, it's a shame I didn't teach you grade 11, but I do it right here, and I get the kids to try to stab it, and they like get it aimed up, and then they close their eyes, and it's always high, like you always miss it high, right here. Okay, what if you're not outside? What if you're laying on the bottom, as one does?
Yes.
That's where you want to be on the exam day. Just laying on the bottom of the pool, relaxing.
at the bottom of it.
What do you see? Like if there's if you look up to the surface, you know what? If you're underwater and you look up at the surface, how many people have ever done that before? Okay, what do you see when you look up? You see light and kind of like blurry reflections and stuff. If you look to the edge, can you see all the way to the edge?
Nah.
No, what happens?
Snell's window.
It just gets kind of shiny, right? So what happens is you see this sort of circle on the surface, and past here is just shiny reflection. But you can kind of see the whole thing. Like you can see the edge. If there's a palm tree out here, you can see it over here. Why? Yeah, that's right there. Because all the light that is coming in is refracting down. So the light from here comes over and goes down to you, and everything from here comes over and goes down to you. But stuff from here, there's nothing that can get to you from here, because it would have had to go more than 90. So you just see like a circle, and then there's nothing outside of that circle. So what's the critical angle, as Pran said? Mm-hmm. So if you get to a point where you go farther and farther out, like this angle comes down more and more, and it goes to a place where it's 90, it actually like won't come out, right? Okay, and then this is something I also should have showed you, but the critical angle makes more sense with thin film. Not thin film. Total internal reflection. Do you guys know what that is?
Yes.
So let's say you have a fiber optic cable, and you shoot a beam straight from what you're like inside the fiber optic cable. You're like with Miss Frizzle on the school bus, and it goes like this, and it goes out like that, right?
Yeah.
There's an angle at which it won't get out, right? So if you make this angle more, it'll be like just above the surface like that. But if you angle it any more, then what happens?
It comes back.
It comes back. It won't refract. It won't leave the fiber. So it just comes back in. And that's how fiber optic cables work. We shoot the light in, and it's thin enough that the light just can't get out, and it stays. Actually, I have a thing.
Is it arc sine and 1 over
It's if you just make the refractive theta, like the angle of refraction, 90, then that internal, the instance. Sorry, let me say this clearly. When theta r, the angle of refraction, is 90, like when this hits 90 degrees from normal, then your angle of incidence is your critical angle. And so if your angle of incidence is any bigger than that, you get total internal reflection. It won't leave. Let me see if I can show this to you.
Benjamin, you're on film.
Busy.
So you have this doodad here.
Yes, a doodad.
Doodads.
Big fan of doodads.
That's right.
They're definitely up there with thingamies.
So you can see this right here, and I have this doodad of plastic. So I don't know if this will work. Let's find out. I'm gonna shine this straight down into this tube, and it wraps around. Let's see if I can.
Should you not shine it at us? Is that not a bad idea?
Can you see it?
Yeah.
Can you see it on the end of the tube?
Yeah.
Yeah.
It's not coming.
Does it shine? Like, does it actually like get out there? I don't know if it'll be
so.
strong enough to.
I can see it.
And if I do it this way, it should work too. Can you see it on the end?
Yeah.
That's super.
So you can't really see it in the tube, right? Why does this not light up red?
because it doesn't come out.
Okay, it never gets out. So if it's not coming out of the tube, you don't see it. So you can't see the light inside of a fiber optic cable. You just see it blinking at the end.
I don't think the laser's not strong enough. It's that the end is like kind of separating light.
Yeah, it's probably diffusing out.
You won't see the light, right?
does that mean you wouldn't see it if it was water either?
Oh yeah, you can see it, but it's pretty. You wouldn't see what, sorry?
You wouldn't see it if that plastic thing was made of water. Like, is it just?
If you could make a tube like this out of water, yeah, it would have a different critical angle, but it would be not too bad. You could probably do it, but that would be pretty impractical.
Yeah.
Yeah, I think it would work, yeah. Okay. Sorry. Okay, so there's a bunch of phase things and this kind of stuff. Oh my. These two graphs, is this simple harmonic? Turn to the person beside you and tell them.
No.
How do you know it's not? How about this one?
No, it's straight.
It's kind of hard to see, but it's dampening. It's getting shorter, so it's not simple harmonic.
The middle one is though, right?
The middle one is, I think.
Yeah, because acceleration and displacement is proportional.
Right, it's going. Where's the acceleration the greatest? If you have a mass on a spring. At the end it's maximum, and in the middle it's zero. How can the acceleration be zero? It's flying through the middle.
Well, speed is maximum.
So the speed is maximum,
And it's slowing down.
but the change in speed is going from speeding up to slowing down. So it passes zero acceleration. That looks like simple harmonic. You guys know all this stuff, how to deal with these graphs?
We'll live.
Okay, you've got energy. So this, turn to the person beside you and describe this. The red line is kinetic, the blue line is potential, and the yellow line is total.
Go.
That one. You find at minimum displacement, you have your maximum velocity and therefore maximum kinetic energy. At your maximum displacement, you have minimum velocity and therefore minimum kinetic energy.
Here, take a look
Conversely,
at the notes. They have everything.
at your maximum displacement, you'll have your maximum acceleration, which is proportional to potential energy in the system. And of course, at your minimum displacement, you have minimum potential energy.
If this is
Benjamin!
very good, Ben. If this is a mass on a spring, what's the middle?
It's this middle.
It's the middle. It's where it's going through. So you have max kinetic, max motion, and no potential. And then at the ends, you have all potential and no kinetic. At any point here, what is the sum of these two?
Total energy.
These will equal the total. And what's happening to the total energy?
Nothing.
Nothing. It's the same.
Some of these two friction and stuff.
Is this going to happen often in the real world?
No, never.
Well,
Friction's not exactly.
I mean, planetary orbits and things like that. So you probably know all that stuff. The nature, science, blah blah blah. Oh, why is this not simple harmonic? This one.
Because there is
There's an asymptote, isn't there?
It's not
It's gonna go up.
straight, right? So remember, the acceleration has to be proportional to what? Negative displacement. It has to be proportional. It can't curve. What does this mean? What's happening here? It's accelerating hard at the end, but then it's instead of a constant change in acceleration with displacement, it's getting pulled more at the end and then less in the middle.
Mm-hmm. Yeah.
So it's kind of like it would be as if you had a spring on the end and you're like compressing the spring and then shooting out, but there's some free space in the middle where it's not really, there's no force on it. Something like that. Okay. Traveling waves. What is a wave? Do you guys know about these things?
Mostly.
What, this one?
Yeah, the example you just lost gave would work because it has to be like linear, then flat, then not linear.
Well, what is it then?
No clue.
Well, it doesn't work. It's not simple harmonic anyway. I'm trying to think of an example of how that would be. Like you need an acceleration that's strong at the end, but gradually tapers off as you go through the middle.
Magnetic field something.
Oh, that could be, yeah, if it's non-constant magnetic field, like if it's a gradient. Could be that. Like that idea. Okay. So we're traveling wave. You guys know the waves on the string and all that stuff?
Yeah.
What about a standing wave? Do you know that?
Is that when both sides are being?
Can you go over harmonics?
Yeah.
Yes. Let me see if there's a good picture I can use here. Okay, do we do the app thing? Did I show you the app with the reflecting waves on the string? We should do it again. Is that what you're telling me? Let's do it again. That waves on the string. Remember this?
We did this.
Let's see. We can make it work. So let's have no damping. We'll have high tension.
Yeah, double slip is hard.
You have to move the thing. Oh, alright. Okay.
Well, listeners, we'll be going over double slip after this, right?
Yeah.
Okay. It's final.
Yeah, I don't understand. Yeah. What was it called? Oh, static waves. I'm gonna go over static waves.
That's what I'm doing right now. So this is wave on a string. It's a string of beads just so that you can see the different positions in the wave. If you whip a string up and down like this, you get this wave moving through the medium. Notice that this is straight until the wave gets there. So that initial up force carries along and lifts the particle in front as it moves. So this particle is sitting still, minding its own business, but it's about to get pulled up. Okay, and the wave is therefore traveling forward. But it's not the particles traveling forward, it's just the energy traveling forward. It's going to hit the end, and it's a fixed end, so what's going to happen?
Down.
Yes, that's correct, Eric. When this gets to the end, it's not going to be able to pull the fixed end up, so it's going to pull itself down. Just Newton's third law, right? So let's carry it. Now, this is going to look weird, but what's happening in this part now?
The reflected wave.
You got the reflected wave, and the reflected wave is moving backwards, and this part is still moving forwards, and it hasn't met the reflected wave yet. So you get that interference happening. You get constructive interference and you get destructive interference, and it keeps interfering. Now, is this going to be a standing wave? I don't think so.
No.
It's going to look really weird. It's close.
Oh, I see.
It's actually close, but you can see there's a little gap in it, right?
Is that because the path difference isn't?
Yeah, you have to have it in phase. So let's try to change it. We can figure this out. What it was. It's just two interfering waves. Is that closer or worse? Oh, well, that's close. That's close.
You might be better off doing a pulse, because then it does one, like it does the do and then it goes. Oh,
That's really close. I'm gonna just restart this. Let's see if this works. Oh, it's close. It's close. We'll keep it at that. It's a little bit out, but it's close. Okay, so this is now close to a standing wave. I would take the time. We don't have time. Is this one wave or two? This is two waves that are interfering. One is going forward, and the other is reflecting back. This and this and this are called what? These are nodes. So what's actually happening there? Is it just that the thing's just sitting still?
They're just
So this is peaks moving past troughs, right? And as they move past each other, it's always the same. It's always the same sum. It always sums to 0. Okay. Okay, and then what happens in what would we call this?
antinode.
This is an antinode. And what's happening there? You have constructors. Exactly. You have peaks moving past each other, and you get the big peak, and you have troughs moving past each other, you get the big trough. So that's what a standing wave is. Now, if you get a really big standing wave, you can get what's called a harmonic. Right? And so you guys know the pipe thing, right? We did this, right? Okay, so you heard the, right? I showed Angie the other day. What has to happen here to get that harmonic sound out of the top of this? And why do we have this all? What's the water for? Yeah, that's right, Peron. The water is just the closed end of the tube. And then we can just adjust the length of the closed end tube, right? So if you get to the right distance of open end and closed end, you can achieve a harmonic. Should I make one? Or do we?
We
You don't
trust you.
Okay.
So it's just whatever.
I'll see if I can make one. Why don't we calculate what it would be? Did anybody see the tuning forks? They're in like a little black. They're somewhere in this classroom. There's a lot of what? There are a lot of things in this classroom, it's true, and they're all over the place. I kind of keep it together until the IAs, and then
Physics
Okay.
Olympics didn't help.
I'm gonna pretend I have a tuning fork, and I go ding, and it's like you can barely hear it, and then when you get to the harmonic, you hear this, right? And if you don't move it down, it disappears, and if you move it up, it goes, and if you move it too high up, it goes nothing. And so it's only at one distance that you get your harmonic, right? So the harmonic is a bit louder sound, but why is it making a louder sound? Because it's making this, right? Now, very important. Sound is what type of wave? It's a longitudinal wave. It's this, right? So a speaker is really just a thing that's moving up and down. That's literally all it is. It's just pushing air forward and back at a whatever frequency. If you slow a speaker right down, like I have that frequency generator thing, and if you slow it down to like 2 hertz, you can see the thing going, right? And then you speed it up, and it goes, and you can't see it, but it's just pushing air. How does that turn into sound? It's only in here. Sound does not exist until you get the electrical signals. Sound's not, it doesn't really exist at all.
Hold on, how do you get
Sound is living in a simulation.
Should have put on the
I won't go
now
there.
that don't
Jake
really
won't let me go there today.
And how do you get like hearing loss?
Well, there's a number of ways.
No, let's not get into hearing loss. Let's
Yeah,
let's continue
fair,
with waves.
fair. So sound is really just compression of air. What's this? What do we call the space between the compressions? That's good. Thank you, Ryan. Rarefaction. Everyone say rarefaction. So you have places in your, if this is the pipe with your water here, you'll have areas of real compression, and maybe there's a compression down here, and in here you have, so this would be called a compression, which I'm assuming you understand, and then this part where it's stretched out is called a rarefaction. Then you have compression, rarefaction, and that's what makes sound. It literally just, the compressed air hits your eardrum and just moves it. And then we have all this doodads in there to turn that into sound in our brain. What you want is well, I don't know what you want, but to get a harmonic, you need to have constructive interference here. So you have to have a compression that's moving down meet a compression that's moving up. And if you get that, the compressions and the rarefactions will constructively interfere as they move past each other. It's a nice way to get a standing wave as a reflection because the waves will have the same wavelength and the same frequency. So as they move past, if you get a compression to meet a compression, it will also meet the trough and the next compression, and it'll just keep going, right? What's the shortest distance that we can have to get a harmonic relative to our wavelength? Tell the person beside you.
Go.
Lambda over 4.
Quarter of a wavelength.
Quarter of a wavelength.
But that's specifically for these ones, with the closed end.
Yes.
Different
Because when it hits the denser medium at the closed
Since
end,
this thing is
it has a
and close at the
1
angle,
pi phase shift. So then you only have to go a quarter down, a quarter up, because you got a half of the wavelength by the phase shift.
3 pi over 4.
Yeah.
Oh, 52 minutes.
Yeah. My phone is dying right now.
Okay. This is part 2 of waves. It's very scatter, but that's how things go. Okay, so first of all, don't forget what happens when you're reflecting off a more dense surface. You get a phase change, right? So it's often drawn not like a compression, it's often drawn as a transverse wave. This is not a transverse wave in real life, it's really a longitudinal wave. But if you come down like, let's do it, how can we draw it? I'll say like coming down like this. So if this is a peak, it's gonna come down, and instead of going back as a peak, it's going to go back as a trough. So it's going to reverse direction and go like this. This one is moving down and this one is moving up. And when well actually, will that be right? No, it'll go back the other way. Because what should happen is this is going from a peak. If this is a peak, it should be transferring back to a trough, right? But it's not gonna. It goes back the other way, and it just goes back this way. That's kind of how you should think of it, really. Sometimes they draw it like that, though, which is weird. But it's got to be peaks lining up with peaks and troughs lining up with troughs. So as this wave here comes down, it's moving down. It's coming back at the same thing. So these peaks, when this trough comes down, this trough will meet it. So you're going peak, trough, peak, trough, peak, trough, which is really compression, rarefaction, compression, rarefaction. And that's what makes that loud sound. Say it again. This is a quarter of a wavelength, actually. It would be a half if you did not have the phase change. Because then you would be going, you'd have your compression, you'd go half down to like equilibrium, and then you'd come back as a trough, right? So if there was no phase change, a half a wavelength would be, would it be?
Yeah, but the phase change
But
is
you
like
get-
you get to skip a half a wave.
That's right, yeah. You also have to remember that it takes time to go down and come back, right? So if you're a peak going in, and you go half a wavelength down and half a wavelength back out, you'll be a peak again, right? So if there's no phase change, half a wavelength would be correct. Does that make sense? Because your peak would come down, like, here. Look at this wave right here. From this peak, a half a wavelength is right here, right? It's a trough. So you'd be a trough at the bottom of the tube, but by the time you got back, so this is down to the bottom, back out would be a peak, right? So if there's no phase change, half a wavelength gives you a harmonic. But there is a phase change by 180 degrees. So you don't need the half a wavelength, you only need a quarter wavelength. Because instead of coming down here and going to a trough, you come down and then you bounce back up to a peak. Does that make sense? Sorry, it's not a great explanation, but hopefully you get it. So this is 1/4 lambda. That's where you get your harmonic. Where's the next harmonic?
3/4.
3/4. You gotta add another half a wavelength so that you go down and come back and you've done a full phase shift. Okay. It's weird to think about, but there's also this graph that you should know. Oh,
You know the
did I
graph.
erase my circles?
Do I know the graph?
I don't know. Do you know the graph?
I don't know if I do know the graph.
Which graph?
I don't know.
Oh,
That's the issue.
where's my circles?
Uh-oh.
I have way too many graphs.
Go.
So close. Adios.
Okay, there's this graph. It's in here somewhere.
That's not funny.
And it's a sound wave graph. Oh, here it is right here. This is often ends up on the exam.
Oh no.
Oh, you can't see it. Sorry. It's drawn like a transverse wave, but it's not a transverse wave. It's a longitudinal wave. This is a compression. This is a rarefaction. Okay. Well, sorry, no, that's not right. You tell me where the compression is and where the rarefaction is.
Wait.
Because this is displacement, and this is distance, not time.
The compression is 2 and 4.
No, choose a compression, 4's a rarefaction because they're going apart.
That's right. This is a weird one, and they often put it on here because they know it's weird, and they know it's a mind bend. So they put it on to see if you can think about it. This is compression. This is a rarefaction.
Because the arrows are pointed. Like,
They're not going to give you the arrows. They're going to ask you to draw the arrows. What they're going to give you is these particles right here. So this is the position of the particles on this graph. It's weird. So this up is not up. It's to the right. And this is not down. It's to the left. So this particle is to the left of its equilibrium position, and this particle is to the right of its equilibrium position. So if this particle is left of its equilibrium and this particle is right of its equilibrium, they're squished together. You understand?
Yes.
Ben gets it. Over here, this particle, remember, is like this is right. Think of this as right or forward displacement. This is left. It's not up and down. is that it's not this wave, it's this wave. Okay. So over here, this particle is to the right of its position. This particle is to the left of its position. So here, these two particles on either side are pushed apart. So this is a rarefaction. That makes sense?
Difference in the compression.
Who's asking the question?
goes down.
How is the compression different? Like I get more.
How is this different
Yeah.
than this?
I mean, I know the visual difference, but how would you like if that one's still right of the.
Yeah, so you have to ask yourself, look at from this particle's point of view, and look in front of it, and look behind it. In front, this thing is to the left of its position.
You guys are on film, just saying.
Oh.
This guy is up here, so it's to the right of its position.
You're coming in through the
you're
left channel
squishing-
audio.
It's getting squished. This particle is at equilibrium, it's just like where it would normally be. But the particles around it are squishing closer to it. For this guy, he's at equilibrium, he's just chilling. But the guy behind him is pushed to the left, and the guy in front of him is pushed to the right. So he's got room around him. He's rarefied. Daniel.
I can't really visualize this. Could you draw the corresponding graph?
Well, you know what we should do is let's draw the particles. So this particle is at equilibrium, right? He's sitting there. But this particle right here is not in its equilibrium position. It's 5 to the right. So this guy would be here, but he's pushed forward. He's actually here. Okay. This guy's at equilibrium. He's here. This particle would be here at equilibrium, but he's 5 to the left. So he's actually this way. He's actually sitting here. Does that make sense?
Should just flip it vertically.
Maybe. And then this guy here is at equilibrium. This guy is pushed, he would be here, but he's been pushed to the right because this value is high. So he's actually over here. So you can just see, this guy's sitting is there's nobody around him, right? So this is rarefied. This is compressed.
You're right. See? That was the diffraction, it's that.
Eric.
That's only for longitudinal.
Yes, only for longitudinal. Are you gonna have like in a water wave? Are you gonna have compressed particles and rarefied
one?
particles?
Yeah.
That's also
Like
super
actually a little bit.
We get
But
that.
if it's a true
It's
transverse
super
wave,
important.
you're not gonna have that.
But you can't compress water.
You can't.
Oh, we didn't even talk about polarizers.
Happens all the time.
That's fine. Polarizers are
That's why
simple.
those people died on that submarine.
Okay, they're not that simple.
Wait, why is he talking about people dying on submarines?
That's the compression.
Oh, right, okay. I was not paying attention for a tiny amount of time when he talks about people being squished in submarines.
Submarine and it went squish.
Ah, yes.
It did the soda can thing.
What's it called? What was it called? Ocean Gate? Is it
Yeah.
Ocean Gate?
How does more pressure mean more compressed?
Or was it Titan?
Yeah, the Titan
Okay.
submarine. Did you just say
that's
that?
a good one to know.
Why does more
You guys
compression mean
want to
it's
go
more
over the
compressed?
single slit, double slit?
Yeah.
How does that make any sense?
Jeffrey's special.
He's Jeffrey.
So you got sound stuff, longitudinal compression, rarefaction. You got the harmonics. Remember the speed of sound is around 333,
40, 340.
340. Did they say 340?
Mhm.
43.
340, depending on the situation. They'll probably give it to you. But remember that the speed of sound will not change unless the medium changes.
Yeah.
So it doesn't matter, if you're moving or whatever, reflection, whatever. It's always gonna be the same speed. What about sonic booms? Do you understand that? Sometimes they ask about that. Yeah, if you're flying in a jet and you're making wave fronts at 340, as you're flying faster, that wavelength, this one goes out and you make the next one, but you move in between the making of the next one, so you shorten, right? And if you get fast enough, you make the wave, but you move at the same speed as the wave, so you make another one, and you make another one, and you make another one. And so what happens is this super compression. You're not allowed to do it over land because it busts everybody's windows. That's what a sonic boom is this super compression of all these waves piling up on each other. That happens when you're crossing the sound barrier. What happens when you go faster than the speed of sound?
Well, that's when you just it's back here and you emit one.
Yeah, you make the wave and you move in front of it, and then you make another one and you move in front of that one. So then it's fine. It's loud, but there's no problem. Right? So you can fly supersonic over land. You just can't break the sound barrier. So if you're in Miramar and you have a mission in Syria, you go out over the Pacific, you break the sound barrier, and then you fly back over at Mach 2 or whatever, 1.5.
So so if you go at the speed of sound for a longer period of time, that wave will have a bigger magnitude, right? Because it will be on top of each other.
If you fly at the speed of sound, yes.
Yeah.
And there's a pushback. You don't want to do that very long.
Yeah, I have an idea for what that.
It shreds your plane apart. That's Andy.
When you've flown down past the sound barrier.
Jeffrey's planning.
Yeah, same thing.
He always is.
It generally happens
Always looks
faster
like-
because it's acceleration at those speeds is tough. Forward acceleration because there's so much force against you. So you tend to sit at the speed of sound for a time. Because you're like going really fast, going a little bit faster, boom, right? And then you're like, go a little bit faster, right? And you leave it. But when you're slowing down, it's like, I'm slowing down, and I hit the speed of sound, boom, and then it goes, and you're like, and you slow down really quickly. So going through it on the slowing down side is usually easier than the speeding up side. But yeah, it's the same concept. Yes.
Can we really quickly cover diffraction?
Diffraction. Thank you.
And also double slit.
And single slit.
Yeah, and single slit.
And
I think
single slit
isn't
mod-
single
Well,
slit
that's all the same
HL?
thing. Right?
No.
No?
And single slit modulation of the double slit.
Okay, so this is in.
We've got 3 minutes, I think.
3 minutes. Oh man.
No,
Okay.
Or is it
8 minutes.
55?
8 minutes.
8
I'll
minutes.
just ditch the book and
That's
we'll just
plenty.
do it. Okay. Remember, diffraction is all about. It's about Huygens principle. So light is really, we say, a whole bunch of an infinite number of wavelets. So it's not one wavefront, it's a bunch of little wavelets being made. And we say if there's the barrier like this, and here's our screen up here, maybe I'll draw this a little bit lower, sorry. Here's your barrier with your two slits, and it's all about that path difference. You remember this? So if you put them together, you're going to have this maximum in the middle because your two waves are essentially coming together. Your peaks line up with peaks and troughs line up with troughs. As the beams start to edge over, you remember you put your elbows on the desk and you move, you're going to have this path difference, right? At what point do you get another bright spot? Good. When you get one wavelength of path difference, right? So when this and this, when the path difference, remember we drew it like a right triangle like this. So if these two are the same, you'll get a constructive interference here if the path difference equals one wavelength, right? And then we said the theta of this is the theta here, and it was, what was it, d sine theta? Lambda equals d sine theta, I believe. That makes sense, doesn't it? And d being
It'll be n lambda.
He's studying
in lambda, yeah. So you'll keep making maxima at when this happens. It's 2 lambda and 3 lambda or whatever until it's not going to
That was 7 years ago.
You don't see it.
Pretty ancient. That was 8 years ago. I can't do math.
For failing it.
I'm failing it so bad.
Oh yeah, they use
What?
Yeah.
Because sine lambda.
Oh yeah, because this is the hypotenuse, yeah, and this is your opposite, right?
Good thing they figured it out.
Okay, so this with 2 slit, this makes a maximum, right?
What is the n?
N is just like 1, 2, 3, 4 integers. So if it's 1 wavelength, it's gonna be d sine theta.
And then
If you move this over and this becomes 2 lambda, then d sine theta of this will give you your second maximum.
Where did you say theta was like equal to on the screen?
Theta's here.
Yeah, but where was it?
So if I draw straight up and this way, this angle is theta. You can work it out because this is right next to that. Jeffrey, what did you say?
I am bothering B about it.
Okay. This is double slit. So with double slit, when d sine theta equals lambda, you get a maximum, right? What happens in single slit?
D sine theta equals lambda is a minimum. D.
So for double slit refraction,
See.
when d sine theta equals lambda, you get a bright spot maximum. If you do this with single slit, so let's say that you just get rid of the stuff in the middle, and this is a full slot. Then what happens, you can draw the same triangle, but now your average path difference, if this path difference is lambda, then your average path difference across the whole slit is half lambda. So now your average path difference is equal to lambda over 2. So for single slit, you can use the same equation, but what does it result in?
A minimum.
A minimum dark spot. So when lambda equals d sine theta in a single slit, you're going to get darkness. And you're going to get a maximum when this is 2 lambda, right? So you have 2 lambda
Yeah, mostly.
equals d sine theta. You will get, so that gives you a minimum, and this gives you a maximum. And then do you remember we had modulation of double slit by single slit?
Yes.
Because when you have a double slit, each slit is a single slit. Yeah. So you have your maximum will look like, say like this. These individual maxima are due to the double slit, but the intensity goes down because each of the slits is a single slit, and so you'll get like this kind of, and so you can actually get like a small maximas out here due to the single slit, but it's all modulated by this single slit doodad. Confusing but true. Yes.
So, in the dots or nodes or whatever they're called.
Okay.
In the double slit, those nodes are the parts that are bright, and in the middle they're dark, right? There's no light. There is light, but what I don't understand is like,
Whoa, what do you mean? Say that again.
like this is the center, and then there are 2
Yeah, yeah.
points, right?
Yep.
in the middle, is it completely like dark, or is it just weirdly interfering and it's like not light?
So if we put a diffraction grating, where's my laser? So if you do this, you can see the dots there, right?
Yeah.
So in between is pretty dark, but
Is it pretty dark or completely dark? Because from our
you're
explanation,
talking about here.
Well, that's dark.
That's
because with our explanation of it, we know that the wavelength is going in a gradient, right? So there's a wave going there, there's another wave going there, and they're not in sync with each other, so the wave is like a weird wave. So why do you not see it?
bless you. So you're talking about the interaction between the single slit line and the double slit line?
No, just a single,
That's
like,
why you
just
see,
by
yeah.
itself, the double.
Okay.
So
And you're
it's,
saying why is this like black?
yeah, because it's
This is dark because you're.
Hmm.
Well, it's only gonna be completely dark at like that exact place. Because as your path difference moves, when you get to lambda, you're gonna have the bright spot. When you're at half lambda, your peaks are lining with troughs and your troughs are lining with peaks.
Yeah.
And it's dark.
Yeah.
So at lambda over 2, it's dark. In between, it's like actually not dark. So if we looked at this really carefully, you would see like in between those points, you would have a really dark spot. But actually, like, I can't move my hands holding both things, but like in between,
Do you want to tell one?
I can't do it.
Do you want to tell one?
Well, you get it. In between the things, there's like, there would be dim light.
Okay, now I get it.
It's not like seeable because you really only see where it's like boom constructed.
I have an hour and 20-minute long video.
That's
Friday is probably our last class.
Tuesday.
So I have a challenge for you.
Pass the IB exams.
We have Tuesday.
Yeah, we have Tuesday, but I don't know if people come.
I will come. We will come.
I'm happy to be here, and I have staff meeting after school today. But tomorrow, if you want fit help, I can do that. If you want after school help, I can do that too. And also,
Alright,
bring
probably stop the video now.
your questions from past exams to
Yeah, I'm just
Friday's
gonna stop the
class.
video.